We see here a ray diagram for parallel rays that were actually entering a Petri dish full of water. The demonstration you saw in the video was actually with an acrylic disc, but in this case we had a Petri dish full of water. The angles were measured. Now let's zoom in just a little bit. Okay, the first angle here, the incident angle, is the angle at which the light ray strikes the medium. Now what's that angle? Well, when the light ray strikes here, if we look at this just locally for a very short distance, we see that we're essentially hitting the water at an angle that's equal to the angle made with this tangent line here. Okay, so the angle of the ray with the medium, which would be this angle, which I haven't labeled because we don't really use it, but that's the angle at which the ray hits the medium. Again, you can see that the ray doesn't care about the rest of the circle. The ray cares only about what it sees right here, and all the ray sees right here is pretty much a straight line at the exact place where it hits the medium. Now, that line is tangent to the circle. You should know the geometry of the circle well enough to know that the tangent line is perpendicular to a radial line, so that we construct a tangent perpendicular to the radial line. Actually, we just draw the tangent, and then we draw the radial line out this way, and we measure the angle theta I between the radial line and the incident ray, and that's our angle of incidence. And then by marking the various points on the figure, we see that the refracted angle, or the angle of refraction, is this angle with the same normal, the same radial line, and by measuring and so forth, we determine that this angle is about 32 degrees. So we come out this way at a 32-degree angle. Similarly, we had an incident angle of 23 degrees here, approximately a 16-degree angle of refraction here. Using N2 equals 1.39, which isn't the accurate value, 1.33 is, but pretending that we're going to go along with our previous observation of the index of refraction of water, we can verify these angles. Okay? Of course, the index of refraction out here in air is 1, so we're going from n equals 1 to n equals 1.39. Okay, now, what's going to happen here? If we look at what happens as we go into this circular lens, essentially, it's a water lens, a lens made of water. These angles bend the ray toward a common point. However, they don't reach that common point before they get to the end of the lens and come back out into air. Now, I've drawn the rays as if they were going straight through at this point, but they aren't. Okay, this ray is actually meeting at the tangent line here, and it's going to be refracted back out this way a little bit into the air. And this ray is going to come out and refract back in this direction, away from the normal, because we're going from a medium of higher index of refraction to a medium of lower index of refraction. Here, the ray is bent toward the normal. Snell's law, if applied here, will bend the ray away from normal, back toward the radial line. And the rays won't meet quite as close as it looks like here. It looks like these two rays are going to meet right about here, which is a lot closer to the lens than they actually meet. Now, what happens up to this point is exactly what happens if you shine parallel rays into a round bottle of Coke or Mountain Dew or whatever. And we can see what happens. We shine into Coke. You can't really see the ray coming through, but it does. You see the ray coming through there and shining onto the screen. Okay? If we shine it close enough to the surface, you can kind of see it. But the laser doesn't show up real well on the video camera. So what I can see out here is not necessarily what you can see on the screen. Okay, so again, this is what's happening up to this point, at least, when we shine parallel rays into a bottle of pop.